Alright guys, so today we're just going to start a little bit of numerical integration. Okay, so numerical integration, in other words, is just approximating a shaded area because we aren't given the function. Okay, so the red line there is the function, calculate the shaded area. Well, you don't know what the function is, so what you've got to do is approximate that. Two ways you can do that, using the Trapezium Rule or Simpson's Rule. But what are those? Okay, so let's have a look at the Trapezium Rule. Okay, so the Trapezium Rule is the easiest way to approximate a linear area. Okay, the area, because it's a linear model. All we're doing is just making a whole bunch of trapeziums. So, have a crack at it first. They'll pause the video, but have a crack at it, and then see how you go. Remember to write your working out, because that's going to help you later on. Okay, so looking at this now, what I'm going to do is I'm going to use the four intervals on the bottom here. So I can see there's one of my trapeziums. Here's another of my trapeziums. Here's another of my trapeziums. And here's the last of my trapeziums. Now, as you can see here, I'm underestimating the area, but I'm overestimating the area. I'm overestimating it, but underestimating it. So, hence why we are estimating. We're trying to, those differences we're going to say are offsetting each other. So, to find the area of a trapezium, we go a half times the base, and I'm saying this height is actually the base, so that's 4.5 plus, I'm going to say that's 5.2 times 2, the height. Here's my height, and then I'm going to add that to 5.2, or half times 5.2 plus 5 times 2 plus, and obviously I'd be working across a page, but I'm just running out of space, so I'm just working down, plus a half times 5 plus 4.8 times 2 plus a half lots of 4.8 plus 5.5 times 2, and that's my area. But this is actually, since this is one long equation, this is a half times 2. Well, what I'm trying to do here is these factors. Okay, so I'll just highlight the common factors, and each one of these, there's a half, and each one, there's a 2. So I'm going to take that half times 2 at the very front, and we're going to have 4.5 plus 5.2 plus 5.2 plus 5 plus 5 plus 4.8 plus 4.8 plus 5.5. In other words, what I've actually got is 2 lots of that, 2 lots of that, 2 lots of that, 2 lots of that. Actually, no, sorry, not 2 lots of the last one. Got a bit carried away. But 2 lots of all those other ones. So what we've got is a half times 2, and the 2, remember, is this interval here, this width here, plus 4.5 plus 5.2 times 2 plus 5 times 2 plus 4.8 times 2 plus 5.5. All of these are doubled. And then that there, if you're looking at your formula sheet, is actually your formula for, well, that is the formula for the area of the trapezium. I'll just pause and put that in there. Okay, so as you can see there, we've got a half lots of h, half lots of h, y0, yn, that's the first and the last, and then we've got 2 lots of all the rest of them added together. H is that over that divided by the amount of intervals we have. 8 minus 0 divided by the 4 intervals gives you 2. Anyway, that's the numerical integration with the Trapezium rule. But how can we make that a better estimation? What we could do is actually calculate the same area, but use a smaller intervals. Okay, so try that one. See if you get a roughly the same answer. Now there are obviously pros and cons with this method, but we'll talk about that later on. But have a crack. Once you've done that, check to see if compare your answers. Compare with the people around you. Then have a crack at that exercise there.